Okay, so we are at 2:15, so we're going to go ahead and start our next talk. Our next speaker is Bryan Jansens from the University of British Columbia.
Okay, thank you very much. And before I actually start getting into the slides, I will very quickly just sort of mention the title. You know, it says that the choices of input variables were physics informed. It's possibly more accurate to say that what I have really done here was try to make the choice of input variables inform me about physics, or inform me something about you know, what's going on physically in the atmosphere. So it's a little bit of a misnomer, but I still think it's it kind of captures what I'm trying to do. Just to sort of orient ourselves to the area that I'm focusing on geographically for this work, I'm looking at the province of British Columbia, Canada, which is a westernmost province in Canada on the Pacific coast. On the map you see on the left there, BC is sort of in between Alaska and Washington State. You know, it's not very zoomed in, but you can kind of get an idea just based on the topography you see there that the west coast of BC, well, the whole province really, is very rugged. A lot of mountains, inlets, valleys and ridges, things like that, that make weather forecasting quite difficult, which is a particular problem because that part of the world, you know, particularly during the cold season, in the fall and winter, experiences fairly often extratropical cyclones, which can cause a lot of damage, you know, power outages, significant financial damage, things like that. So we would like to do a better job of forecasting those. And so the reason that I think about using neural networks and deep learning to try to help with that is that the methods, you know, we're currently using can really struggle to capture some of the high impact you know, surface wind events. So what you're seeing here on the right is for 1 month in 2021 for the weather station. Let me just back up for a second here. So the map of BC you see there, if you look at the southwest part of the province, that's what we're zoomed into here, just northwest of the city of Vancouver. That little red dot is the weather station that the plot on the right is showing some results for 1 month in February last year. The blue line in that plot represents observations of that weather station. The red line is a raw forecast from about a 50-member ensemble that my team runs at UBC. And the green line is a post-processed forecast using a Kalman filtering technique. So, you know, when I look at that plot, that's kind of all the motivation I need to try and do something a little bit different, because we're seeing that we're not really capturing the peaks of that wind event at all. So that's my objective, and sort of my big picture objective is to try and use neural networks to make our surface wind speed forecasts, and particularly the post-processing of surface wind speed forecasts by numerical weather prediction models, more accurate. For this particular talk, I was asking a much smaller question, which is, can varying the variables that we put into a neural network as inputs affect how accurate that model is, and can that tell us something about the physics of what's going on in this complex terrain that we can use to make better choices and better forecasts. So for a neural network, I need some inputs, and I need some targets. So the targets that I'm trying to train my network for are observations from Environment Canada, or Environment and Climate Change Canada, weather stations in BC. For this particular study, I narrowed it down to 5 stations, and I'll in fact only be showing results from 2, although I have the others if you're interested to see. Again, this map here is sort of the zoomed in part of southwestern BC. The red markers indicate the locations of the stations that I used. For the inputs to the model, I used output from I used output from the Canadian Global Environmental Model, not the WRF model. This is the GDPS. No, that is WRF model. 3 domains. What I actually used for this this talk is the 3-kilometer domain, the smallest domain centered around Southwest BC and Vancouver Island there. And I've used 5 years of forecasts for training the model 2016 to 2020, and the forecasts from 2021 are used for testing. The variables that I used, which are the ones that I vary, you can see here the selection is mostly variables that are actually output directly by the model, with a few extra derived ones, including the mean wind speed at a few different heights in the atmosphere and the wind direction. As far as the machine learning model, the neural network model that I used, I think the most important thing to take away from this slide is that I was using sort of the very simplest kind of feed-forward neural network model. And as I'll mention when I talk about future work, I think there's some things that could potentially work out a little better for that, but this was sort of like a baseline for what I could do. And I mentioned some of the choices I made in terms of the hyperparameters of the model, tested out some different things, and those worked out best. So that being said, before I show some of the results, I'll just mention that basically what I was trying to assess was how accurate the predictions that this model made were. And in order to do that, I was calculating the mean absolute error, or the MAE, between the predictions and observations after generating predictions on the test set. The two stations that I'm going to show had sufficient high wind speed events as well that I did this for both the entire set of observed winds as well as for higher wind speed events, which in this case I chose 50 kilometers per hour or higher observed winds. For each setup that I used for different input variables, I ran the model 4 different times. And so when you see the results, that's an average of each of those four runs. So the first set of results I'm going to show you is for this station again in Pamrocks, just northwest of Vancouver. What you're seeing in the table here, I've set the results so that the base configuration, which is including all the variables that I listed on that one slide, is set to 0. And everything else, all these other different configurations where I've taken out different variables, used only the WRF output and not the derived variables, things like that. Basically, I've subtracted off the all variables value from what we have here. So what this means is that if you see a positive value, that means that there was more error in that configuration than there was in the all variables baseline. If you see a negative value, that means there was less error. And so what sort of immediately stands out to me in this case is that for this station, removing input variables from the network is actually reducing the error in the model's predictions. So and in particular, what you can interpret these numbers as is that this is more or less that many kilometers per hour, I guess, for how different this configuration is compared to the baseline. So you're becoming you're seeing less error when you're taking out the temperature variables, the wind variables at 70 kilopascals from your inputs. Esteban Point is the other one I wanted to show some results for. That's off the west coast of Vancouver Island, and that in particular is an interesting one because they have some very strong, even hurricane force wind events there at times. And a similar situation there with removing the wind variables for the high wind speed events actually, causes quite a bit more, I should say quite a bit less error per hour. So that was a little bit surprising to me, I suppose. It suggests to me maybe a little bit that having all of those variables in there is leading to some overfitting in that model. But I think also what really stood out to me from working on this is that removing single variables or even combinations of variables was not causing sort of dramatic changes in the predictive power of the model in terms of, the accuracy of the predictions it was making. So, ultimately, to answer the question that I posed on the third slide, at least for this particular model, it doesn't seem like it really affects it that much. So where I really want to take this next, there's two big things I want to do. The first is I want, this was using sort of the straightforward basic feed-forward neural network. Because I'm working with time series here, I feel like using a recurrent neural network would be a really promising way to try and incorporate some of the time information into this work. But especially what I would really like to try and do, for numerical weather modeling in the mountains, the terrain is an obstacle, and the way I like to think about it for this case as well, and if you have all these mountains and valleys and things like that, there's only so many places the wind can be. It's sort of constrained a little bit by the terrain. And if I can, figure out a way to try and incorporate this kind of information into a model, I feel like that could be very useful and very helpful. And so that's kind of the big thing that I want to do next with this. So finally, I'd like to thank my supervisor at UBC, Dr. Roland Stahl, and Dr. Greg West. And I also like to give a special thanks to Yulia Yavorek, who prepared the WRF output data that I used for this talk, as well as the sponsors of my work. So thank you.
Thank you, Bryan. Do we have any questions for Bryan here in the room?
Nice talk, Bryan. One of the things that I could see could improve the match is I looked at the list of variables that you presented rapidly, and I didn't see anything on stability at low levels.
Right.
And I didn't see anything on how well you can represent the complex geography with 3-kilometer resolution. So something I would say a mismatch between the geography that the model thinks is happening versus the actual one. Mm-hmm. And I'm not sure how that could be a standard deviation of heights or something like that. Mm-hmm. You may want to consider this, and I guess I was curious to know why. It would seem that to me that this is what would make the biggest difference between a model forecast and reality in terms of the wind, and that could be a useful input to the machine learning.
Yeah, definitely. I think that what you're talking about, it sounds like is trying to use the model geography, and that's definitely something I would like to do next. I think you're right. I think that would be quite helpful. And like I said, use that geography to our advantage instead of letting it be a hindrance.
We have time for one more quick question.
Okay, so some of the worst predictor variables in your results, like all the wind variables coming out of WRF and the 700 millibar or the 70 kilopascal information, those worst predictor variables would seem to me anyways a priori to be some of the most important information. Like it's kind of counterintuitive. Yeah. That when you're trying to forecast wind, your results get better when you remove the wind forecast from the WRF. Do you have an explanation for why that is? Are the WRF wind forecasts maybe just really bad in that mountainous terrain?
Yeah, so I mean, I don't have an explanation, but I can give some speculation, and I think that's kind of what I've noticed, sort of just in general wind forecasting in BC that. You would think intuitively that a finer resolution model would be better, and oftentimes it isn't. And I think probably it does have something to do with the fact that the winds and the terrain are, not necessarily. It's not forecasting well. And so I think I would agree with that and say that that's kind of what I would speculate as to why that's the case.
Okay, let's go ahead and thank our speaker again. Thank you, Bryan.